handout, the eligibility handout. I got basically a couple. Card, like how that's the cards work. In color, right, in color, just for you all. And I also have this other handout that I thought could be potentially useful. Just showing you how intersections and unions kind of work. We got to do. Finally, practice problem.
Thank you.
Which I will post solutions to. I have written them. I haven't posted it yet, but for those of you not in class, I will also post all these things on Canvas. Oh. As is typical. So actually, I did end up getting an actual copy of the practice file instead of just making it up on my own. So it's pretty much verbatim. You can grab one of those handouts there. The practice final I made up is pretty very similar to the exam he gave last quarter. Notably, the wording on some of the questions, which I think is a little terrible, is pretty similar. So there's a note or two in there about how maybe you should read it. Also some references to sections in the textbook if something is unclear where it's coming from. Like I think problem 7, I wasn't super familiar with the natural killer, whatever thing it is. So, but it was definitely on the exam. So I would of course encourage you. Oh, and then also there was one other thing. Let me make sure here. So I'll post all that at some point and then just to make sure. One other thing I just want to point out. I think it's let's get logged in here. Yeah. It's really all I wanted to point out was that in addition to all those things, there's also a final review on Grant's website. If you look, oh my gosh, can I get there? Maybe. But if you look at our campus, I don't think, do I have it? I'm curious if I have it on here. I don't think so. Oh no, I do have I can just open those up right there. Sure. So I'll make sure those are published, but they're also on Grant's website. Sure, this is published right now while we're here. There's an older practice final that I might publish if I feel like it's worthwhile. I'll take a look at it first though. Just making sure. So let's see. So yeah, I'll look at that practice. But yeah, I might as well. Maybe I'll unpublish this if I decide it's not worthwhile, but it's probably a practice final I wrote for. I don't know when was the last time I did this class. There you go. There's other things. Okay. So lots of things to look at. I guess I can move this up here. Sorry, and this is not the best time to do this, but all right. That's all I want to say about that. It's just that those are there. You have lots of resources before your final that is on Tuesday, Wednesday, Thursday, Sunday next week. With it? Wednesday, all right. As I mentioned, I'll be out of town Wednesday through Friday, but I will be having office hours in the library Monday and Tuesday and Wednesday of next week, which I posted on Canvas. So I think that's just about everything as far as what we're doing. Forgot to print out our attendance sheet, so sure, right, Jamie, on a piece of paper last time. All right, pens. So most of what I thought we should cover today was talking about well, actually, mostly like these problems where like talking about like a disease, like a population having a disease and then testing, like, and then developing a test for like testing if someone has the disease, the test is like turns a positive result this percentage of the time, et cetera, et cetera, et cetera. Did he talk about that in class today? Is that okay? Okay. Interesting. All right. Okay. Give me a second. Blackjack? Okay. So I feel like, yeah, so even though there's stuff to talk about there, I think we should really spend our last day together talking about conditional probability and kind of specifically the disease ones, because I feel like that's just what's most likely to come up on an exam. And there's a pretty easy way of dealing with it. Easiest. There's a pretty straightforward way of dealing with it. So let's do that. Today is the what, 11th, 10th. Um, yeah. We'll start off with this example though. So 1 second. So we'll talk a little bit about conditional probability. So some examples. A family has 2 children. Oh, it's pen. Or maybe it's in my hand. One of them is a girl. What is the probability that both are girls? It might seem like the answer is 1/2. It is not. This is a prime example of how conditional probability kind of alters maybe your mindset or your kind of your framework. So we know one of the kids is a girl. So here's what we know our reduced sample space is. Instead of being boy, 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 girl, girl, boy, girl, girl, right? Those are the 4 possibilities you can have. Our reduced sample space is just going to be, well, we could have either had a boy then a girl, or a girl then a boy, or a girl then a girl. We know we couldn't have had a boy then a boy because we already know one of the kids is a girl. So out of those 3 things, the one we're looking for, probably that both are girls, is GG. So I guess, and I've made not a mistake, but I've done myself a disservice. I should have given these things some names. So if I say, knowing that one is a girl is event A, and trying to find the probability that both are girls being event B, then what I'm trying to find is the probability of B given A. The thing you know always gets written second. So we know A is true. We know one of the kids is a girl. Could be the oldest, could be the youngest. We don't know which. That's actually an important piece of information, that we don't know which child is the oldest or which child is the girl. That's going to be, well, one way of getting what you want. Out of 3 ways of any of these things can happen, 1 out of 3. Or the more formulaic way of doing this is that the probability of B given A is the probability that both happen divided by the probability that the given thing happens. Okay. So for B to happen and A to happen, B is that both are girls. A is that at least one girl. Or sorry, at least one girl. I always felt like this is kind of the funny part, because oftentimes for both of these things to happen, it's just that the thing that you're trying to see if it happens, right? If at least one kid's going to be a girl and both kids are girls, both kids have to be girls. Can't be girl, boy, or boy, girl, right? So the idea here is that essentially all the things in B are wholly contained in set A. So that if you're trying to find B intersect A, well, essentially you've got this situation where B already is in A. So the overlap is just B. That happens a lot in these problems. So don't be too surprised. So what's the probability of getting girl, girl? Well, in the broader context, where any one of the usual four things can happen, boy, boy, or boy, girl, or girl, boy, or girl, girl, then it's a 1 in 4 chance. And the probability of having event A happen where one of the children is a girl, there's 3 out of 4 ways that can happen. And as is usual, this probability ends up being the same no matter which way you think about it. It's good to know how to do it the formulaic way. It's good to know how to do it thinking about the reduced sample space sort of way. I will tell you that when I see this conditional probability formula, my brain usually jumps straight to saying, oh yeah, it's the probability of the overlap over the probability of the given thing. Like this formula, I think, is one you want to know. Even if we don't always use it. I'm trying to think of how the thing I want to happen can happen divided by all the things that can happen. Oh, and yeah, and then we should also say something. So let's actually look at the other situation where we know that the oldest is a girl. So same situation, except now we know the oldest child is a girl. Now what's the probability? Of girl, girl. Well, we can again look at it both ways, but our reduced sample space now is just going to be, it's either going to be girl then boy or girl then girl. We can't have boy girl, right? That's not an option because we know the oldest child is a girl, not just that one of the children is a girl. So in this case, the probability of B given A is just 1 out of 2. Or again, you can do it the longer way, or it's B intersect A divided by the probability of A, which is going to be, there's 2 out of 4 ways of getting an oldest girl, and there's, oh my gosh, okay, I got that backwards. Apologize. Ooh, whoa, 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 whoa. That should be a 1 out of 4 on top. That's how many ways of getting girl, girl. And on the bottom, it's 2 out of 4, which is either girl, boy, or girl, girl, which ends up being 1/2 again. And what I wanted to point out here is, again, if we're talking about the probability of B happening on its own, specifically, in this case, when you're asking if the probability of getting girl, girl, it's the same as asking what's the probability that the youngest child is a girl, since we already know the oldest is a girl. Let's call that event B. What I want you to see here is that the probability that the youngest child is a girl, just on its own, if you knew nothing else, would be 1/2, assuming, right, the typical assumption of a 50-50 probability, right? That might not actually be 100% true, but whatever. It's not the point. So here's what I want you to know. In this problem, unlike the previous problem, events A and B, A being the oldest child being a girl, sorry, I know my labeling is terrible, and B being the youngest child is a girl, these events are independent. The way I always think about this is that knowing that one of the events happens doesn't affect the probability of the other one happening. Or in other words, the probability of B is equal to the probability of B knowing that A happened. This would always be the way I would prefer to think about showing 2 events are independent. That knowing that A happened didn't change the probability of B. Another way people write this, though, is that the probability of B times the probability of A is equal to the probability of the intersection. But if someone ever asks you to show that 2 events are independent, this is the way I usually think about going about it. But you might recognize that this is going to be the same as that because the right side of this formula here is just the probability of A intersect B divided by the probability of A. And if you multiply both sides by the probability of A, this equation would become that equation. So they really are the same equation, just a different way of expressing it. Independence is important because it allows us, so basically independence allows us to like multiply probabilities together, right? If you say that these, like back when we were kind of talking about the way you could choose like, oh my gosh, like a course schedule, and there wasn't really like, all of our choices were independent, like your biology class and your chemistry class, right? Those choices were independent of each other. Making one choice didn't affect the choices we could make for the other things. That's basically the idea of independence, is that knowing other information doesn't affect subsequent steps. So one example of that, and then we'll move along, and then we'll finally get to what I want to do. So here's an example where we're using the independence. A multiple choice test has 10 questions. And each question has 5 possible responses. Let's call them A through E. We'll do question A first. Find the probability of answering all 10 questions correctly simply by guessing, right? When you're doing these kind of questions, the assumption is you don't know anything, so it's an equally probable chance of picking the right one from the four, or not equal, but like each chance has an equal likelihood of being picked. Okay, so that's not too terrible. Well, I mean, it would be terrible if you actually were in that situation, right? You would hope you would not be just be guessing on all 10 questions. But you definitely shouldn't leave any questions blank if you're taking multiple choice tests, right? So here, the probability of getting, I'm going to say X is the number correct. The probability of getting X equal to 10. Well, what's the probability of getting the first one right? 1 out of 5. How about the second one? 1 out of 5. All of them are going to be 1 out of 5. That's going to be 1 out of 5 to the 10th power, which is very small. It's approximately 1.024 times 10 to the negative 7th. So like, I think it's about 1 in 1 million or 1 in 10 million. It's really, really, really unlikely that you're going to guess all of them right. Okay. Here's a more interesting question. What's the probability of getting at least 9 correct? Okay, well, this problem's a little more interesting because, well, first of all, we're going to be adding 2 things together. The probability of getting 9 plus the probability of getting 10. We already know what this part's going to be. This part's going to be 1/5 to the 10th. How about the probability of getting 9 correct? Well, let's say we were going to get the last one wrong. So probably getting the first 9 correct are going to be 1/5 times 1/5 times 1/5 times 1/5 9 times. And then getting the last one wrong means we had to have a probability of 4/5 instead of 1/5, right? We didn't get it right. But who says we have to get the last one wrong, right? Any one of the 10 questions could have been the wrong one we're going to pick to be wrong. So the way we're going to calculate this is going to be the following. It's going to be 10 choose 9. For the 9 we're going to get correct. There's 10 different ways you could pick that. AKA there's 10 different ways you can pick the one you get wrong. Times 1/5 to the 9th power, because we want 9 of them to be correct, and there's a 1/5 probability that each of those 9 are correct. Times 4/5 the first. Which is still not very large. but we'd add those together, and that's what you get. You get 10, right? Because 10 choose 9 is 10, times 1/5 to the 9th, times 4/5 to the 1st, plus 1/5 to the 10th. And just to be absolutely clear about what's going on here, the probability of getting exactly half, half is not my favorite choice here. The probability of getting exactly 6 right. Here's the more general version of what's happening here. If I want to know the probability of getting 6 right, there's 3 pieces. There's the number of ways you can pick the 6 ones you're going to get correct, which is 10 choose 6. And then there's the probability of getting those 6 specific questions right. Well, that's going to be 1/5 raised to the 6th power. And then you have to also get the other 4 wrong. Well, the probability of getting it wrong is 4/5, and the number of wrong ones are going to be 4. I don't know if he has or if he will talk about like a binomial distribution, but this is an example of that, where basically you have a probability of success and a probability of failure, and if you're trying to calculate the probability of X number of successes, this is how you do it. It's the total, well, so let's just write the formula here. If you have N trials and you want X successes, P is the probability of success, and obviously 1 minus P is the probability of failure, then the probability of getting X, it's going to be N choose X times P to the X times 1 minus P to the N minus X. Hopefully you can see that. I feel like that part of the board always looks blurry for me. That's where that's coming from. All right. This definitely does assume that each guess or each trial or each thing you're doing is independent of each other one. All right, let's look at some of this blood test disease stuff, which is really just the context where we talk about what's usually referred to as Bayes rule or Bayes formula. So this is all in the context of Bayes rule / formula, which I do not think you should memorize. I think you should memorize, or not memorize, but you should, and I would say you should utilize a tree, which we will talk about. See if I can pick up this for a second here. Yeah. So these, oh yeah, the way he wrote the test question, I felt like was really super confusing, but so here's the usual kind of setup for problem like this. Let me make sure I'm in the right spot here. Yeah, we're good. Okay. So a blood test for a disease shows, come on in, a positive result in 98% of the cases when the disease is present. And also a positive result in 6% of the cases when the disease is not present, called a false positive. Also, so typically you're given 2 pieces of information in this kind of problem. You're given some sort of probability about how the test works, either when the person has the disease or when they don't have the disease. They could also tell you, they could also give it to you in a less nice way. Like they could tell you that the test shows a negative result in 2% of the cases when the disease is present, right? That would be the same information phrased differently. And they could tell you it gives you and is whatever. Anyway, they also have to tell you something about like how prevalent the disease is. In this case, we're assuming the disease exists in every 1 out of 250 people. We could also give it as a percentage and just decide to be annoying about it. So before I do anything with a problem like this, I would write down some stuff. I would write down names for things. Usually, yeah, I don't love the way. So here's the way he did it on the exam, which I guess I'll go with because I should. So here's the way he wrote it. He said D plus is having the disease and D minus is not having it, which is just not my favorite notation. And then T plus is testing positive. T minus is testing negative. And then we should write down what all the things they told us actually mean. So here's what they've told us so far. They told us we get a positive result, so a T positive, in 98% of the cases where the disease is present. It's really somewhat challenging to read that. Usually the end thing is the given thing. So they're saying if the disease is present, then we get a positive test 98% of the time. Or in other words, the probability of a positive test given that the disease is present is 0.98. That's what that underlined sentence is actually telling us is a conditional probability. If you know someone has the disease, there's a 98% chance that the test will come out positive. Similarly, this next line, and also in 6% of the cases where the disease is not present, meaning we're also going to get a positive test. So a positive test given that the person does not have the disease 6% of the time. Make sure when you write 6% as a decimal, there's a 0.06. I've often made that error. Finally, the disease exists in every 1 out of 10 people, meaning they're just telling you the probability of having the disease. So probability of D plus is 1 out of 250, which you could write as a decimal as 0.004. All right. So first question. What's the probability of testing positive? So when I ask questions like this, I almost always like to make a tree. Because there's basically only like a few things that can happen, especially in these kinds of situations with diseases and tests. The first branch of the tree is usually kind of the thing that's going to be the given information. So usually you are knowing that's not the information that could be given before you took the test. In other words, whether or not you have the disease. So their first branch is either we have the disease or we don't. Here's a good piece of knowledge. Every branch vertically should add up to 100%. If you only have these many choices, all the choices should represent all the possibilities or probabilities. The probability of having the disease is 1 out of 250, or if you prefer, 0.004. The probability of not having the disease is 249 out of 250, or 0.996. And then after that, each of these gets to branch again. If you then take the test to see if you have the disease, there's only 2 possibilities. You get a positive test or you get a negative test. Now, these probabilities of these possibilities are based on what we found up here. The probability of a positive test given a positive disease is going to be 0.98. But the nice thing about that, and I really do think this is nicer than trying to like write it out, it also tells you what this other one's going to be. If we know the probability of a positive test given a positive disease is 0.98, we know the probability of a negative test given that someone has the disease is 0.02. And similarly, if we know the probability of a positive test given not having the disease is 0.06, then we know the probability of having a negative test given that someone doesn't have the disease is going to be 0.94. It has to add up to 1 in each branching. And now here's what makes this great. To answer the question, probability of testing positive, you just have to follow all the paths that get you to a positive test. So just writing it out, the probability of a positive test is going to be, well, this first branch here, which I would normally not write out the letters, I would just write out the numbers, but I'm going to write the letters here. So it's going to be the probability of first testing positive, sorry, having the disease, but I don't like this notation, multiplied by the probability of testing positive, given that you have the disease. Plus the other path to get you there, the probability of testing negative times the probability of this. I hate this notation so much. Sorry. The probability of not having the disease times the probability of testing positive, given that you do not have the disease. Yeah. I am only choosing to use this notation because it was what I saw in the practice final, and I guess we should practice doing it that way if you're going to see it that way, even though it's terrible. So then we fill in the numbers. It's going to be probability of D plus, so 0.004 times this, which is 0.98, plus this, which is 0.996, times that, which is 0.06. Not too terrible. Which ends up being approximately 0.0638. I don't really care about this number. On an exam, you would definitely leave it like this. But it's interesting to notice that the probability of testing positive is pretty close to the same as the probability of a false positive. Since the disease is so not prevalent, it's actually the false positive that are giving you most of the positives here, and the actual that have the disease, not so much. So make sure I'm in the right spot here. No. Okay, so the question that I think is the most interesting or the most useful is the following. What's the probability of having the disease given that we tested positive? Or in other words, if I test positive, how likely is it that I actually have the disease? Because that's actually what you want to know, right? Like if you're taking this test, you're taking this test because you don't know if you have this disease or not. And so you're saying, okay, well, I got a positive test. Do I actually have this disease? Should I test again? Well, let's find out. And the thing that I think is interesting here is that most people that are not familiar with statistics or haven't seen this kind of thing before would make a guess, and hopefully this example doesn't prove me wrong, but it doesn't prove me. But like most people would guess, well, it's probably like 0.98 because right, the probability of a positive test given that you have the disease is 98%. So it seems like the probability of having the disease given a positive test should also be that, but it's usually actually not at all the same, which is kind of interesting. So let's find out. So what I'm trying to find here is the probability of having the disease given that we had a positive test. And again, this is where the formula that I think of in my head for a conditional probability is the first step, and then the tree is the second step. So here's really the only step I actually want to write out formulaically. The probability of having disease and given that we had a positive test is the probability of having the disease and having a positive test divided by the probability of a positive test. And honestly, here's the work I would do. And here's the way I would think about this. So every time you follow a path on your tree, all of the individual branch numbers multiply together. Because if I'm trying to get to having a disease and, oh, the magic word and means we multiply things together, a positive test, it's going to be this branch multiplied by that branch. On the other hand, if I just want to have a positive test, I want to find all the paths to get me to a positive test. So it's either this branch, where it's this and this, or, oh, I said the other magic word, or that means we're going to add the things together, this and this. So I wouldn't really write, so I'm going to skip writing all the formulas out here and I'll write them in a minute. But really, here's what I would jump to. I'd say, cool, it's this first path. That's going to be 0.004 times a 0.98. The probability of having the disease and then having a positive test given that I have the disease divided by all the ways I can have a positive test, which we just calculated before. That's going to be 0.004 times 0.98, which is the probability of, again, having the disease and a positive test, plus 0.996 times 0.06, the probability of not having the disease and still having a positive test. By the way, those are the only ways you can have a positive test. You can either have the disease and a positive test, or not have the disease and a positive test. Oh my gosh, it's called the rule of total probability, I think. Or if you want to find like all the ways of getting something, you basically say, well, it's all the ways of getting this thing and any of the other things it gets paired with. So here, probability of having a positive test, it gets paired with either having the disease or not having the disease, and those never overlap, right? They're very mutually exclusive, non-overlapping. So then if we calculated this, and I don't think I have these numbers on me, so I'll just grab the calculator here. I do actually want to find this number. Where'd you go, calculator? I know you were in there when I looked earlier. There you are. This is at the bottom. So on top we have 0.004 times 0.98. By the way, I will point out this example is one though where you can't just do it like the reduced sample space like we were doing those earlier ones. Where I say we can think of it this way or this way. This kind of example, you really have to go from this part of the formula to this part of the formula. Like you don't have a choice really, unlike our previous ones. So we're going to get about 0.00392 divided by 0.0638. The bottom number is an approximation. I don't like approximations, so I'm going to actually do it. We get about 0.062. So, contrary to what we might have thought before, the probability of having the disease given that you have a positive test is about 6.2%. Nowhere near the 98% positive test given that you have the disease percentage. So, not a very high chance of actually having the disease given that you have a positive test because the disease itself is not very prevalent. That is the more influencing factor on our outcome here. Okay, let's see. Trying to think about which time is here. Let's see if I can find one more good question here. The disease, I feel like the disease one's not the most important, really, but I'm trying to think. I just don't want to do like the same exact thing again, although I guess we could, but oh, that one's kind of not terrible. Sorry. So many examples to choose from. No, not you. All right, let's look at the same sort of example. There is one other thing that comes up for me. But honestly, if I had to wager, I would guess he would ask you one like this because he literally did on the past exam. And it's just a very common situation. Oh, I know. Sorry, I know. I forgot to actually talk about the formula. So just as kind of to go a little bit more into this, when you talk about this formula here, the probability of having the disease and a positive test divided by the probability of having a positive test. You can get more formulaic with this if you want to. And I will point out, I'm still just basing this all on the tree. So here's what I'm really doing. I know that for having the disease and a positive test, looking back at my tree, you see all that? Not really. I don't know. Sorry, it's terrible. You can see it all. So maybe, sure. Okay, so for disease and positive test, first we take the path of disease, then we multiply by the path of positive test given that you already have the disease. So it's the probability of that conditional probability there. Again, all these things we already wrote down at the very beginning of this problem. or we could have found. In the bottom here, first the law of total probability, it's having a positive test and having the disease, plus having a positive test and not having the disease. And then we can again use this idea here that, oh, it's just going to be the same numerator. And then literally, so I'll point out, I wrote this in the backwards order. It doesn't really matter. The order you write the intersection, A intersect B or B intersect A, the overlap is the same no matter which order you write it in. Not true for conditional probabilities, as we've just seen, right? It matters which one of these things goes first in a conditional probability. But then the bottom here, well, this part here is just the same as that part right there. So I'm just going to get this same numerator. Probability of having the disease times the probability of a positive test given that we have the disease, plus, oops, I wrote the wrong thing here. I apologize. This should be a not having the disease, not having a negative test. Sorry about that. This is going to be the probability of not having the disease times the probability of a positive test given that we didn't have the disease. I probably still haven't actually memorized this formula in my many years of teaching this because it's just so much easier for me to think about drawing a tree diagram and saying, cool, it's the things I want, having a disease and a positive test divided by all the things I'm trying to be out of, which is just having a positive test, which is all the ways I get to having a positive test. So in case I hadn't made it clear already, I really, really, really think you should draw a tree when you do this problem. Really. Yeah. Sure, we'll do this. We probably have enough time. Okay, I'm going to use slightly easier notation for me so that we can do this next problem in the 7 minutes we have left instead of trying to make it. Oh gosh, maybe not. So, sorry, I know I'm all over the place here. So here's the next situation, which is similar but has an extra kind of level of spice to it. This is 3. I'm just going to write down the relevant things here. So, a rare disease affects 1 out of 1,000 people. So that's its prevalence. The probability of a positive test for someone affected is 99%. The probability of a negative test for someone unaffected is 2%. Sorry, 98%. Sorry about that. We're going to find a few things here. But first, let's write down all we know. The first question, what do we know? Or what probabilities do we know? So usually the way I like to write this is D is the event of having the disease. Sure I can spell. D complement is how I like to say the not having disease is not having it. And then I usually use a plus for testing positive and a minus for testing negative. That's just how lots of people do it. So what do we know? Well, we know that the probability of having the disease or the prevalence is just 1 out of 1,000 or 0.001. We know the probability of a positive test for someone affected is 99%. So the probability of a positive test given that someone has the disease is 99%. And the probability of a negative test for someone unaffected is 98%. So the probability of a negative test, given that someone does not have the disease, is 98%. I will also point out, even without drawing the tree, you could fill in the other two pieces of information that we weren't told explicitly, but should be relatively obvious. This is telling us that, well, if we know the probability of a positive test given they have the disease is 99%, then the probability of a negative test given that they have the disease should be 1%. Similarly, the probability of a positive test given that they do not have the disease should be 2%. Or in other words, the probability of a false positive is 2%. The probability of a false negative is 1%. The false negative is when you falsely test negative. False positive is when you falsely test positive. All right. Sure, let's skip that since we only have a few minutes left. So, yeah, still a good question. What is the probability of having the disease if we tested positive? I want you all to draw a tree. Yeah. Yes, I can. No, you're good. I'm going a little too fast. All right, so I'd love to give you more time, but I'm almost out. Almost always on these questions, I always think of the first branch as the branch is usually like if they've told you some conditional probabilities, it is the given thing in those conditional probabilities. In both of our conditional probabilities, it was given that we either had the disease or didn't have the disease. So those should be the events that go in your first branch. So it doesn't matter which side you put them on. You have the disease here and not having the disease here. And then their associated probabilities, which were 1 out of 1,000 or 0.001, and the rest, 0.999. And then the probability of having a positive test when you have the disease, and that's positive here, negative here, was 0.99 for a positive test and 0.01 for a negative test. And for a positive test and a negative test, given we didn't have the disease, it was 0.02 for one of them. I'm like, yeah. Yeah, it was 0.02 up here and 0.90 down. So then if we're trying to find the probability of having the disease given a positive test, again, I do think writing this first formulaic part is necessary. I need to write it. It's disease and positive test divided by the probability of having a positive test. And that's going to be all the ways you get that, which is just this pathway here. So 0.001 times 0.99. divided by this pathway plus this pathway. So 0.001 times 0.99 plus 0.999 divided by 0.02. And then you could leave it like that, but if you have a calculator, want to know, it's going to be, let's see, 0.001 times 0.99 plus 0.999 times 0.02, and then we're getting about 0.047. So just another reminder that, yeah, even though the probability of having a positive test, given that you have the disease, is quite high, right? The test is very accurate. That doesn't mean you have the disease if you test positive necessarily, right? It's a much lower chance of actually having it because, again, the disease itself is not very prevalent. All right, that is all I have for you. As I said in the beginning, I'll make sure all the things are posted. Also try to find a few more relevant videos from other quarters about probability stuff in case there's other things we didn't get to talk about. Looking at the final if you look at the practice final I posted, there's only a couple. There's like one probability question like this, and there's another probability-ish question about like, or counting question about like the number of boys or girls a wolf can have. That's not to say, so again, not to say that your exam is going to look exactly like that, right? He could write something different, but I would imagine it'll be in a similar vein to the questions that are on there. You're obviously welcome to message me if you have questions. I have office hours today and tomorrow as usual, and then gone Wednesday through Friday, back Monday through Thursday in the library for drop-in hours, which are posted. My drop-in hours are posted in the announcement on Canvas. So take a look there if you're looking for me specifically. But honestly, every day, either Grant or myself will be there like from 11 to 4. So you'll be able to get help, as well as student tutors. All right, that's all I got. Good luck on your finals.